Good morning, everyone. Welcome to the presentation from iSize. My name is Yannis Andreopoulos, and I am the technical director of the company. We are an AI technology company that develops solutions for optimizing video delivery over existing standards. And today we'll be talking about perceptually optimized AI-based video delivery without breaking standards and dependencies that exist today in the industry. The motivation of our work is the fact that encoding hits a complexity wall, as has been quoted on the slide by David Ronca, who's a director at Facebook. What does that mean? It means that when you are basically moving to new generations of encoders from, let's say, AVC to HEVC to VP9, AV1, VVC, and beyond, complexity begins to exponentiate for encoding, as you can see in the blue curve, and at the same time, the gains in compression efficiency begin to saturate, right? That is not a good situation for sustainability, for power, for heat dissipation, for cloud-based scaling, and so on, right? So, at the same time, what has happened is that traditional quality measurement in encoding has been done using things like peak signal to noise ratio or structural similarity and so on. But in the last 5 to 7 years, the industry has begun moving more to perceptually optimized encoding using open metrics such as VMAF and VIF and others, as well as SSIM, which is structural similarity, because they are closer to encapsulating human perception, right? So the question is, could we leverage on the fact that we have new quality scoring mechanisms, better ways of capturing human perception, and use that for the benefit of reducing encoding complexity, improving bitrate efficiency, especially as we move to newer standards, right? And the situation is challenging because encoders are amazing, signal to noise ratio or structural similarity machines, but these quality metrics, as I mentioned, they're not the best to capture perceptual quality in video, right? So what are we proposing here? We're proposing that AI has a place in video encoding as either a pre-processing mechanism before the encoder or potentially a post-processing mechanism after the decoder in order to optimize quality before it goes into onward transcoding or potentially display on a mobile device or a desktop or a TV, right? Now, what does that mean here? When we have a server-side enhancement, the idea of an AI framework would be to be applied in a number of ways. Let's go through and understand what these ways could be, right? One way is to do ML or neural network optimization of existing encoder recipes on top of standards, right? So AVC, HEVC, AV1, VVC, and beyond. Now, these approaches are standard compliant, but operate under a strict SNR SSIM optimization regime, and they don't optimize for new perceptual metrics, right? At the same time, they need reimplementation for every encoder and every vendor, and that's complex to deploy at scale, especially for large services that could be using multiple standards and multiple vendors implementing those standards, right? An alternative would be to abandon standards and move to neural encoders. The challenge there is, while they've been proposed for the last 8 years, they are not compliant to any existing formats, and the performance still fails to outperform even optimized HEVC under advanced configurations for encoding tools, right? So the question is, would it be a very big risk, even if they would outperform existing standards, which is a very open question? You would need to move into new formats, new packaging, new encoding, decoding mechanisms. Devices can overheat from decoders, needing GPUs and so on, right? So that makes neural encoders not necessarily the best way to do things. Other approaches are using an AI framework for perceptual optimization of encoders and optimizing not anymore for signal to noise ratio, but instead for quality metrics like VMAF and more perceptually oriented encoding, right? So the problem there is that such optimizers need to be need to be applied for each encoding. They typically improve on one metric, but when they do so, they damage every other quality metric, and that's not a desirable situation because one would like to improve across multiple metrics, right? And the improvement is typically only in certain regimes of bitrate and quality, where it is not always quantifiable or visible, right? Last but not least, recent proposals in metrics have made them more robust for such metric-oriented optimization. So that's also not a very desirable situation to go into. So finding overall the best rate perception distortion and complexity trade-off that would optimize the encoder complexity by a preprocessor is a hard problem, right? Now, what we are proposing is basically an AI psychovisual preprocessor that is tuned to human vision, not necessarily a specific metric. It is applied across multiple standards. It is not requiring changes in formats, in metadata, in packaging, in transport, and so on, and certainly no changes in decoders and devices, right? The 5 principles of such a design, in our view, are here. The first is that such a preprocessor must encapsulate known principles of human vision in a data-driven or learnable way. The second is it should offer benefits over multiple existing state-of-the-art metrics and quality measured in a subjective manner in lab testing such as P910 tests and so on. It should apply across content from gaming to sports to animation and across encoders from AVC, legacy encoding to HEVC to AV1 and beyond. Delay is a big issue, so it shouldn't buffer and need, increasing delay to seconds or even milliseconds if possible. And last but not least, it shouldn't increase the complexity of the overall implementation, right? So in fact, the inference complexity, the runtime complexity should be comparable to an AVC, let's say, encoder that you can find out there. So we have such a solution at iSize, which you can come to our booth later, which is down the hall here to have a look at our demos. And we call it BitSave, right? So we believe it meets those 5 pillars of the design that would make it a generalized AI-based psychovisual preprocessor. And it's because it is a very low delay solution. It only touches the content once, and then you can encode with multiple encoders, multiple recipes at multiple bit rates for an entire ABR ladder. It improves over multiple quality metrics, so not just, let's say, SSIM, but also VMAF and VIF and others. And it can work in tandem with other solutions we have, such as denoisers at the decoder, which we're going to touch upon in a minute, right? In terms of integration, we have partnered with Intel and NVIDIA to optimize inference through OpenVINO, NNX, and similar frameworks. It supports HDR, Dolby Vision formats, and others, and it's very easy to plug and play with any existing workflow, right? Now, this is a high-level design slide of the framework, which I will only briefly go over. The idea of designing and training such an AI solution centers in getting multiple frames of test content, passing them through a neural network that is trained for pre-processing, and then the processed content goes into a virtual encoder here, which basically emulates a typical operation of a standard, okay? A typical DCT, block-based prediction, entropy encoding, and so on. The output of this is effectively a rate measurement that says what is the expected rate to encode the processed content and what is the quality we get when we measure versus the input using, for example, visualizations of metrics such as mean square error, SSIM, VMAF, and so on. We can make that into a perceptual loss and train end-to-end, so backpropagate through the quality scoring, through the virtual encoder, and through our preprocessor in order to change the neural network weights of the preprocessor design and optimize it, okay? Then, when we want to deploy it in production, we simply take the preprocessor here and plug in an actual encoder with an actual encoding recipe, such as H.264, HEVC, AV1, and beyond, right? And that actually tends to work quite well. In terms of numbers, we have done extensive tests with our partners using state-of-the-art encoding recipes over multiple standards from AVC to VP9 to AV1 here. So what you see here on the horizontal axis is encoding complexity in a log scale. So 10 to the power 4, 10,000 seconds, 10 to the power 5 seconds, a million seconds, 10 million seconds and so on, to encode a big workload here, right? Now, the next part relates to quality, and quality here is measured in terms of a score that relates to human perception, and we call it a P910 MOS score. What does that mean? It means that we're collecting multiple metrics such as VMAF, SSIM, VIF, and other metrics. We are also correlating them with tests we have done in the lab for subjective testing with P910 and DCR, ACR measurements, and then creating a score per encoder that scores the quality. Now, when we get the quality here, we do bit rate measurements, which tells us for each of the encoding presets of an encoder what is the average rate increase versus a reference point. So for example, the best possible encoder you can find for a large workload today would be something like SVT-AV1 preset 0, right? That's the anchor point here. That's the slowest encoder, which obviously is the reference of 0, it's the most efficient one, right? You cannot save beyond this with a conventional framework. If you use VP9, VP9 is less efficient than AV1, and you can see for different presets, you have a bitrate overhead versus AV1 from 40% to 70% and so on. And AVC, of course, versus AV1 highly optimized encoding, the bitrate overhead can be 100% or beyond, right? These are encoding presets from slower to faster presets and so on. Now, if you enable our preprocessing solution, which is an AI optimized preprocessor for vision of human viewers, you get the savings you see here. So for example, we make even the most efficient encoder gain an additional about 10%, which increases to 15% or even more at the faster encoding settings. For other encoders, the savings we get are 15% to 25% or beyond, as you can see here with the green curves. And interestingly enough, complexity is not increased in any substantial manner, okay? So for the same preset, we have almost the same complexity, if not even a little bit less. What's interesting is you can trade off bitrate savings for compute efficiency of encoding, right? For example, versus the M2 preset of SVT-AV1, we can offer the same bitrate efficiency, but being 5 times more efficient and so on, right? This is for an encoding VOD workload, but the same applies to live and other solutions. These are average savings we have calculated together with our industrial partners. For cloud gaming, it's particularly efficient. This is a very typical use case for us. Here's an example of a game that you can see on the left side, our preprocessor with NVENC HEVC versus HEVC X265. And you see for the same quality, we can offer about 20% saving from 4 megabits down to 3.2 megabits, right? Without any detriment in quality as measured in VMAF here. And we have more demos that you can come to our booth and have a look, right? Now, in terms of deployment, a typical use case would be, for example, a live game streaming service that would like to reduce the bitrate by 20%, allow more users to be admitted for the bandwidth allocation that they have, improve quality of service, improve storage efficiency, and so on, right? The solution would be to deploy our BitSave SDK with, for example, NVIDIA GPU ABR ladder scaling for multi-bitrate encoding in HLS or WebRTC. In the results, we show that it reduces in practical tests live game streaming bitrate by an average of 20% over the entire ABR ladder. It allows for the same or even slightly better improved quality at that saving with latency cost, which is minimal, about 2 milliseconds for 1080p or even 4K resolutions on NVIDIA GPUs, right? And obviously the benefits are that the quality of experience increases, they can admit more users to their service, and it can deliver up to 30x return of investment for the cost of deploying this, right? We have also moved such technologies to the decoder, and now we can post-process content after decoding, either on mobile devices or on servers prior to transcoding. Again, very low latency solution, single pass processing for all the bitrate ladder, and it improves quality metrics and visual quality. And I'm going to show you a quick example. This is the noisy content that was decoded on the right, and this is what we can recover with the BitClear post-processor. And you can see the quality improvement is quite dramatic, right? Of improving from what the decoder decoded. And you know, I'm going to leave this slide up as a summary of the benefits we have seen in our practical deployments. Please come to our booth at 9200 here in the West Hall, and we'll be happy to walk you through the demos and explain the technology in a deeper way. Thank you very much for your attention.